Okay, welcome everyone, and good morning, good afternoon, and good evening to everyone, and welcome to hydraulic modeling in premise plumbing systems. So we have 6 speakers already. And also if you, for better presentation, please mute yourself. We will appreciate it, and then we'll move on from there. So for today's agenda, a very brief introduction, and then followed by about 80 minutes of a presentation, total 6 presentations. Very exciting topics today related to hydraulics, hydraulic modeling, and water demand related with the hydraulic modeling as well. And then followed by 20 minutes of a Q&A session and also the research needs. And then as you see, as you all know well, please use the chat button. Please feel free to your comments and then questions in there, and we'll try to address during the discussion session. So brief purpose of the PPM Premise Plumbing Modeling Test Committee. So we formed this test committee to advance the science of new field of premise plumbing modeling. So objective is to document the state of the art and then identify the future research and development needs. And then we're going to prepare a report and then other mechanisms for disseminating information. And also we are working on the chapter. Each webinar will be the chapter, and then we're going to come up with the committee report, which will eventually be the book publication. So if you're interested in contributing to chapter, please feel free to contact the webinar coordinator and myself, please. The next one is we already did 3 webinars, very successful webinars so far. And then today will be the hydraulic modeling. And then each month there will be the webinars as shown in this slide. Also, we created a premise plumbing modeling YouTube channel. So please feel free to subscribe and then hit the like button if you like it. So the YouTube, you just go to the YouTube and then type in premise plumbing modeling, and then all our previous recorded webinars are available. So having said that, so let me start with my first talk. So I will be talking about hydraulic transient in premise plumbing. So as you all know, this shows the overall schematic for the layout of water mains, service lines, and then premise plumbing. So now for this talk, I would like to focus on the service lines. Okay, why study service lines? It is known that up to 30 to 40% of the water is lost due to leaks, and then service lines is known to be the weakest spot, and also the responsible for largest volume of real water losses. So there's a significant water quality issues, which is including lower total chlorine residuals, short detention time before potential consumption, and then lead service lines as well. And also there's a liability issues because that's the property of homeowners or building owners. So the objective of this talk that I'm delivering today is to measure pressure variation at various locations within the premise plumbing system and service lines, and also to evaluate cavitation phenomena for both steady state and transient state, and then also the validate numerical method. So right now we have a simple scenarios that can happen. The transient can happen at the service line. As you can see in this figure, so transient 1, we define that as transient triggered within the household, including the laundry, dish machines, like that. And also transient 2, that is triggered from upstream of the household. And then transient 3, triggered from downstream of the household, the premise plumbing. So we built the experiment to simulate the transient, hydraulic transient that can happen at service line. So this shows the vertical section cables we built in the lab. And then this shows the solenoid valve tree to simulate the sudden closure, sudden opening of the valve, and shows the flow meter, and also the clear plastic pipe section to demonstrate to video record the possible cavitation, including gaseous cavitation and vaporous cavitation inside the pipeline. And this shows the regular pressure gauges. And also we use the DEC system, DAQ systems with the LabVIEW-based data acquisition systems. And then this shows the flow meter power supply. And also this is the T-junction with the pressure transducers. And then all the data is connected, fed to the AQ system. So result, this shows the scenario 1, which is a transient triggered within the household. So when we suddenly close it, and please note that the y-axis is only the delta of pressure. We use the dynamic pressure transducer, meaning 0 means there's no zero, almost zero pressure variations, which is steady state. And then there's a sudden fluctuation due to valve closing, pressure spike, which is the, you can see, read it as about delta of 70 psi gauge pressure due to valve closing. So we can see that due to this sudden closure and opening, the service line is constantly taxed in terms of a physical integrity of the service line pipe or pipe materials. And also the scenario 2, so transient triggered from the upstream of the premise plumbing. So as you see here, these pressure variations, and please note that the steady state values was about 40 psi gauge pressure. And then when we suddenly close it, it is experiencing almost negative 50 psi gauge pressure, just a delta of negative 50, meaning at the service line can easily experience up to negative 10 or negative 12 gauge pressure inside the service line. So scenario 3, very similar patterns, but the magnitude is a little bit smaller. So when there's a sudden closure from the downstream of the premise plumbing, we see the pressure variations due to closing. We see some spike about 25, 30, and also the opening, of course, there will be some pressure reduction. So this is also one of the interesting results that we observed. So when we observe the pressure variation at the vertical section with a dead end on it, we observed very high significant pressure variations, about 120 pressure spike at the vertical section with a dead end. We believe that has an implication for high-rise buildings pressure variation due to transients triggered within the building itself. So that may early failure, that may be correlated, but we did not prove it, but at least it shows that vertical section transient is behaving more interestingly at that location. So, and also, as mentioned, transient due to transient triggered at the upstream of the water mains, and then the service line is going through, as mentioned, this is a pressure variation y-axis, so negative 50 psi, so meaning the service line is experiencing almost negative 10 to negative 12 pressure gauge pressures inside the service line. And then at the same time, we recorded the phenomena through the clear plastic pipe. Whenever the low pressure happens, we observe the cavitation. We suspect that is a gaseous cavitation due to water hammer induced pressure drop inside the service line, simulated service line. That was interesting as well. So after we did have the observation values, we tried to validate using numerical method. This shows the classical continuity momentum equations. And then we use the 3 different numerical methods using a method of characteristics, explicit and then implicit schemes. So for the scenario 2, which we observed about negative 12 psi gauge pressure, and we observed via calibrating, we could have the similar result for all the numerical method. So, okay. So the next experiment that I'm going to introduce is, because as mentioned, service line is like a Achilles heel within water distribution system. It's a weak spot. It has the largest volume of real water losses at the service line. I asked myself, why? What's the problem? My hypothesis was pressure might be the culprit for the early failure or large failure at the service line. So we spent about more than $10,000 for purchasing and installing these simulated T-junctions. That this part shows the water mains, and then this part, branched one, shows simulating transient service lines. And then we installed various transducers at different locations because I suspect that location might play a role. Here's the result. So depending on this is P5, 6, 7, 8, 9, 10, that shows the location of pressure transducer that we installed at the T-junction. And then due to sudden closure, upstream closure of the butterfly valve that we installed. And then this shows the steady state was a 60 PSI. And then for different locations, to our a little bit of a disappointment, we didn't see huge fluctuation or huge differences according to location of the service line. So which bears a further examination. And then this shows the simulated leaks. Of course, as we know well, so if there's a leak, the fluctuation is somewhat smoothed out. That's also what we observed. So the summary in it, so for hydraulic tension from the water main has a high potential to result in sufficiently low pressure at service lines to cause possible intrusion of microbial and then chemical contaminants, and also physical integrity of service line and then hydraulic integrity at water main should be maintained with the utmost effort to protect any possible human health risk involved with our homeowners or building owners' property, which is service line. So in that manner, the educational outreach should be developed so public citizens are aware of these issues, including water utility personnel, home builders, and then public health officials. Okay, and then this one figure is showing our ongoing research effort. And then as you all know very well, so the water quality is very complex. So pH, temperature, stagnant water, or high velocity water, and also their impact on free chlorine, TTHM, DBP, HPC, or Legionella. Not much is known. Right now, we are using EPA-NET and an EPA-NET MSX. As you also know, that's based on steady state extended period simulation modeling. But now that gives us the research question in the following slide, which is how do we measure the impact of hydraulic transient on chemical and biological water quality changes? I believe not much is known about this area. And also, how do we link the water quality behaviors with the transient in modeling? So is it EPS, extended period simulation modeling? Is it enough? That's questionable. And then how do we link gaseous cavitation or vaporous cavitation with the water quality changes in premise plumbing? I personally very much suspect that banging sound or noisy plumbing system, as well as a milky water, that might be correlated very significantly with the gaseous cavitation or possibly vaporous cavitation in our plumbing system as well. So those are the research questions that I have in mind, and hopefully we can continue our discussion at the end of our webinar. Now I'm going to turn over my talk to Dr. James Gong, and he's the professor at Deakin University. James, please.
Oh, good, thank you. I'm James Gong. Now I'm based at Deakin University in Australia. So Deakin has multiple campuses, and my campus is based in Geelong, which is a city just next to Melbourne. So today the talk is about a work we've done about 3 years ago. So it can be considered as origin for why I'm entering into the plumbing system analysis. I've been doing transient analysis for water distribution systems for more than 10 years. About 3 years ago, I noticed that the plumbing system actually interact with the water distribution system a lot, and sometimes it's much more complex. So that inspired me to do more work on the plumbing side in collaboration with Phil Woodhouse, who will talk a bit more after me, and also in collaboration with Professor Martin Lambert at the University of Adelaide. So I will give a very brief background introduction of where the work was conducted, and then talk about the transient pressure data we collected and how we characterize the transients with the focus of understanding the source of the transient events. Then we did some research in terms of mitigating the transient impact. So back in 2017, South Australian Water, SA Water, invested more than 4 million Australian dollars, which is about 3 million US dollars, I think, to establish the very first smart water network in Australia. And it is quite, substantial actually in terms of the number of sensors and the type of sensors. Here in my talk today, the focus is on the pressure transient logging. This is, as I said, its origin. So we noticed a number of issues based on the pressure measurements. And one of the extension is the leak before break application for pipe break early warning, which is discussed in a journal paper. So this is a map of the CBD area in Adelaide. So it's about 2 by 2.5 kilometer square. So within this network, about 125 kilometers of water mains, we have 20 permanently installed pressure sensors, pressure loggers. In the previous slide, you may notice that I mentioned 23 pressure loggers. So 3 of them have been used as the mobile loggers. So 20 have been used as the permanent loggers and 3 as mobile loggers. They measure at 128 Hertz continuously, 24/7, and the data were transmitted through the 3G network to a cloud server. The results I presented here were from the data collected between December 2016 to June 2017. So the very first finding was the city water network actually was quite noisy. It's much more, it's much noisier than people would think. And more interestingly, we can see that within this, 2 by 2.5 kilometer area, not very large, right? But we see some of the areas, some parts of the area has much more, transient activities, much more than the other area. So here in the middle of the city and next to the Victoria Square, which is a large square, then we have the central market. So that's the heart of the city. Lots of restaurants, high-rise buildings. So this area is the most, the busiest area in Adelaide, and as expected, lots of water usage and transients happening. Then in terms of the type of transient source, building water service operations, this is a major contributor to the transients we observed in the water distribution network. The fire system operations, again, these are in the buildings. The buildings, especially the multi-level buildings, they have to go through regular fire system testings. Then the last one is pipe bursts. This not very often, a few, every month probably. So here we go to some of the details. So this shows one of the transient event we logged using the permanent and also some of the mobile loggers. So the building water operations, as mentioned, that contributes to more than 85% of all the events we logged. And most of them really small, less than 10 meters, but some of them can be large. So, about 30 meters. And note that the standing pressure there in Adelaide is about 55 meters. The fire system testing, again, this from the buildings, especially the high-rise buildings. In Adelaide, I think it is required that all the buildings have to do the fire system testing at minimum once a month. some of the buildings do every week. Some of them do every fortnight. So in the city there's so many high-rise buildings, so this just keeps coming pretty much every day. You can see something like this. The pressure drop for quite a few meters at multiple locations and last for 30 to 60 meters, then back up. Then we one thing we did was trying to find the source of some of the significant transient events, because we worry about the impact to the city network. So these are from the buildings, as we understood. So we try to locate the buildings. Then we use the permanent loggers and also some of the mobile loggers to triangulate the events based on the wave speed and the time of arrival. This is one of the examples. You can see this building making lots of transients fairly frequent. Every maybe 2-3 minutes, we have a transient event, and it's quite significant. So this is an enlarged view of the one of the transient event. So you can say using the mobile loggers, we can have a better understanding of the scale of the problem. So here we see the variation is about 30 meters, if you check this dotted line here. But if we do not have the mobile loggers, if we just rely on the permanent loggers, we may only see a few meters variation and we may just ignore it. Then we visited a few buildings. It's quite interesting, actually, quite an experience, because as you know, water utilities don't really have any control after the meter. So the meter is a boundary. Okay, before the meter, that's the water utilities jurisdiction. After the meter, that's private property. So getting access to the buildings, is difficult in the first place. And here we found some of the contributors to the transients. So pumps, the electric and also diesel pumps, without any transient protection or without any soft starters, they are the main contributors to the transients, as we observed in the city network. And another interesting thing during the visits, some of the visits, was that the building owners or the managers, they told us that, oh, okay, good to know. Well, we just had a failure, not long ago, and we keep having some, noise out of the plumbing system, and we couldn't figure out why. So they do have issues, and I feel, later after my talk, we'll talk more on their part, on the building part. Then we did a following research in terms of suppressing the peak pressure. So we know, the buildings contribute to most of the transient events, but water utilities can't really do much, inside the buildings, because it's out of their control. So we're thinking, okay, can we do something on the water distribution side, on this part of the meter? So here we consider a water main, which is along the street, and we have a branch going to a building, for example. So we compared the original condition, which is all metallic. So this is to simulate a DN150 cast iron pipe with a wave speed of 1200 meters per second. Then we say if we have a pulse signal, okay, pressure wave, which was induced by close and then open this valve with a discharge of 10 liters per second, we would have a pressure transient about 20 meters. Okay, if it's all metallic pipe, we will have a transient wave about 20 meters. If we replace a section of the metallic pipe by plastic pipe with the same or similar diameter, and connect the branch onto the plastic section, not to the metallic section, we will see the for the same water usage event, we would not have that significant pressure variations on the water main. So basically what happens is the impedance difference between the plastic pipe and the metallic pipe will force the wave to bounce between these two boundaries. And that helps to distribute the energy across a number of pulses, not a single pulse. So if we further increase the size of the pipe, the size of the plastic pipe, so that will further reduce the impedance of this section, this plastic section. So that will further help, reducing the peak pressure. So there is a question for all of you to think about after this. So here we just presented, you can see a smart use of plastic pipe in combination with metallic pipe. So what if not so smart use of pipes that are made of different materials or with different impedance? So here I summarize the findings and the needs. I'm not going through all of this, but the takeaway message is our water distribution system actually noisier than you thought. And our buildings are the main contributor to the transient events in water distribution systems. And this has huge implications. So on the building side and also on the water distribution side. So there are so many questions to ask. Here I just posed two. So one is, how do we quantify the impact of small or moderate but frequent hydraulic transients? Some work has been done, I have noticed in the UK in particular. So what we have done in the past couple of years was leak before break. So what we suspect was these transient events contribute to small crack growth in aging metallic pipes in particular. And those small cracks, initially they are very small and probably just a small leak that nobody knows. Then they will grow to a bigger one, and eventually they will become large enough and burst the pipe. So the observation through the transient logging has inspired us to do the leak detection, for pipe break early warning, but we haven't really figured out the physics behind, exactly how those transient events contribute to the pipe crack and the pipe break later. Then the other question is, how do we bridge the gap between water utilities and plumbers? So basically, the meter is the boundary. On this side, that's the water distribution system. On that side, that's plumbing system. And people do not talk to each other. So that's the biggest, one of the big issues here. So that's all for my presentation, and happy to have further discussion later.
All right, thank you very much, James. Appreciate it. Our next speaker will be Phil Woolhouse from Phil Woolhouse Hydraulics in Australia. Phil.
Okay, can everyone hear me okay now?
Yes, perfect.
All right. So hello everyone, and just a short little bit of history about who I am. Plumbing is not only my profession, it's my hobby, it's my passion, and for a while it's been an obsession. I started in the industry at the age of 16 about 35 years ago, and I was trained not to fix something until I understood why it failed in the first place. 10 years ago, I became interested in why we were having so many piping system failures within Australia. And since then, I've become one of the leading experts in hot water circulation failures. The key to my success in discovering the reasons for these failures was the use of measurement. Have you ever wondered what the water pressure gets to when you hear that noise of the toilet cistern when it stops filling? These are the little things that interest me, so I measure them. And this is my brother's house, and it reached 1,000 kPa transient when the cistern filled. But what was more interesting was the 50-odd 160 kPa pressure drops that were occurring about every second for about 2/100ths of a second. So every time I measure something, I find something new. For more than 10 years now in Australia, we have been having significant issues with increasing pipe failures in many buildings. This slide is just some of the media reports that are making the papers about some of the problems. Now, whether they be burst pipes or water quality such as lead or heavy metals or Legionella, our plumbing systems are definitely under more scrutiny than ever before. At first, a certain type of materials got the blame as they were the first things to fail. But over time, it became more apparent that all materials are experiencing very similar issues. And I ask, why now? So the common problems that I encounter, and I often relate my work to looking at pipe failures a little bit like aircraft investigation. A plane does not normally crash due to the failure of a single component. It's normally a multitude of problems that occur simultaneously. A perfect storm is another good description. The common problems that I see normally start from a combination of the design and the quality of the installation. Then the factors that I find operating in the system, well, they range from about these 7 most common problems. One is entrained air, and this leads to two-phase flows and turbulence. I see issues with velocity, both high and low. Cavitation, obviously from the velocity and the turbulence of the air. Oxidization or corrosion due to high levels of chlorine, copper, or oxygen. And high temperatures. Temperature is a key driver for all types of corrosion, and it helps produce air out of the water. Pressure instability is what I'm going to talk about today. And of course, this water hammer, which was visible at my brother's house, but is no longer heard due to all the acoustic absorbing materials that we now use in our plumbing systems. The more of these factors that are occurring simultaneously, the shorter the plumbing system will last. And just removing one factor can remove several other problems at one time. So while I'm talking about pressure stability, I want you to think about some tiny little air pockets that will be in our piping systems and what they will be doing. So why now? So why have these problems becoming more prevalent in modern systems? And how have our systems changed? So here's a quick overview into the components that we now use and how that they've changed the pressure dynamics. And I'm going to start with the backflow valve. And the backflow valves do a wonderful job of protecting our systems from contamination from back siphonage. But the dual-loaded spring checks in these valves can subject our systems to multiple pressure spikes and water transients. I often say we fix one problem only to create another. Thermal expansion from water heaters. We use cold water expansion valves in Australia on our water heaters instead of expansion tanks. So our system pressures can quite easily go to 3 or 4 times the normal static pressure when the water is heated. And this dwelling had a static pressure of around 300 kPa and the thermal expansion valve was 1200, and you can see that the pressures reached 1200 kPa sometime for many hours, especially if there's no leaks within their system. And we have temperature mixing valves, and I think these are common throughout the world to prevent hot water scalding. The valve mixes both hot and cold water to provide a safe mix temperature at the outlet. But what happens when these valves have 1200 kPa on the hot side and only 300 kPa on the cold? Well, the small 10-cent little plastic check valve that sits in there quite frequently fails. And now we get high pressure hot water now travels into the cold. If the system can't get back into the street mains, then the cold water pressure, like it did in this dwelling, will also go to whatever the pressure is driven from the hot water heater. So we can now have double our water pressure above the standard within our systems. Or we can lead to other problems. like unintentional heating of cold water, increasing the rate of microbial growth. Air removal. Air is a major problem within our piping systems, but when we take it out, it also creates issues. I removed all the air from this building in the hot water system, only to discover every time the electric element turned on and heated the water 5 degrees C, we ended up with a 500 kPa rise in pressure. So on May the 4th, we installed a hot water expansion tank. So I fixed one problem, I created another. Pressure reduction valves. What's wrong with gravity? The Romans didn't seem to have a problem with it, and now all we do is invent mechanical devices that try and defy it. This graph represents a PRV installed on a street system that had severe cyclic pressures. The dark blue line here is the pressure profile over 5 days, taken at frequencies of every 2 seconds. The green line is finally when the plumber finally got the PRV commissioned correctly, and we were able to cut down the maximum pressure. But what we found is we actually increased the intensity of the cyclic pressure within the building. So we fixed one thing, but we created another. Variable speed pressure pumps. My problem is not with the pump technology. We can get very stable pressures from variable speed drive pumps if they are sized correctly for the low flow most frequently experienced in our building. Unfortunately, this is not normally the case. In this building, there were two things. The plumber did not commission the pumps correctly. They were oversized, three things actually, and they did not release all the air from the system. These pumps were sitting on the top of a 20-story building and generated significant cyclic activity. The pressure reduction valves at the bottom of the building burst their diaphragms and exposed the apartments at the base to very high water pressures, causing leaks to occur in a building just a week after opening. So we combine all of these devices into one, and what do we get? We get damaging dynamics. This client's building was less than 8 years old. Their circulated hot water system, their piping had been replaced twice and failed again. It was just been replaced for the third time. The cold water pipes in the ground had burst more than a number of times, 2 I think it was. The water tanks had already been replaced and they soon need replacing again. From one of our previous presentations, I heard someone say that people act in very predictable ways, but our plumbing systems may necessarily not. So in summary, the occurrence of premise plumbing pipe or system failures are increasing significantly in commercial buildings. Water pressures in modern buildings are more variable due to the introduction of multiple fast closing valves and equipment. Common oversizing of pressure pumps, pipes and valves to cater for peak flows compound and increase the cyclic pressure rate when systems are operating at low flows. Pressure variations can have a significant effect in reducing the life of a piping system when combined with entrained air pockets, high temperature and mechanical stress. Plumbing systems require permanent data monitoring to analyse these system operation and identify problems when they occur. And I'm mostly referring to large commercial buildings when I say that. And finally, potential discussion questions. How does cyclic water pressure have an effect on the water quality and changes in premise plumbing? How do we address the use of modern equipment that increases pressure instability or cyclic behaviour? And how do we link the water quality behaviour with cyclic water pressures in modelling? I've often found that when we get a lot of cyclic pressures occurring, we get a lot of forward and reverse flows occurring in the building, and then we get issues of high lead levels with the water coming into contact with the brass. So I'm Phil Woolhouse. Thanks for listening. I hope you enjoyed my presentation.
Absolutely. Thank you very much. I feel appreciated. All right. Our next speaker will be Olivier Pillar from INRAE ETBX. So Olivier, please.
So my presentation is more about what kind of model we can use for designing the network. Because together with Jeroen Doyerlein, we are making some software developments, and we would like to share what we have understood and what we don't know for pre-mass plumbing modeling. So here it is a small example of copper tube, 1.5 centimeter. You can see there are some horizontal pipe, some vertical pipe. There are some minor loss because of the bends and so on. And when we are looking for the energy conservation on the horizontal pipe, the difference of pressure head is explained by the frictional head loss and the sum of the minor head loss. And on the vertical pipes, we have to add the weight of water, so the difference of elevation here. If we look what are doing the solver, so they are using a solver like EPNet is using the piezometric head. So in place of using the pressure head, they are directly using the pressure head more the elevation. So this is white. This can be used for horizontal pipe and vertical pipes. So here this is with the Tonini notation, and this is for all complex system, pre-mass plumbing modeling, and it is working well also for pre-mass plumbing for the conservation of energy. There were several speakers today speaking about transient, but it was more related with the pressure waves and the damage it can cause. There is also a transient which is between steady states, two steady states, and here there is a mass oscillation phenomenon. So what is changing here is that we are just looking for period of 30 minutes. And the EPNet solver is using steady states, and that term is forgot. Also here this is the derivation of the flow with time, with some initial term, the length, and this is divided by the acceleration here and the cross-sectional area. So if we want to understand the mass oscillation, for example, with the toilet that we can get, this is like a small tanks, we have to have that term here. If you want to understand how it is flowing inside the system when there are some taps open or closed and the toilets simultaneously, we have to use that kind of system. And also, if you want to understand the water quality, because the velocity in pipes is used by the water quality system. So here this is just some possibility how to solve that rigid water column model by simple theta scheme. So we have done that in the past. I'm not sure there are some kind of solver available easily. They are in Canada, maybe Jonathan Nolt with Warren Carney are doing some kind of research. We have done that at ISTA, and my colleague Jeroen Doyerlein also has a solver for just calculating the mass oscillation, not the pressure wave. Okay, so here this is some issue that are related to the water quality. In EPNet, there is a water quality component which is transported in the system. with the velocity from an EPS solver. So my feeling is that we need to have something more sophisticated, like the rigid water column here. And also there are some phenomena because the water in the tubes is not always in movement. So there are molecular dispersion. If you are interested to study the security of the system and the pollution, but also for water age. This is a long time ago. We know what kind of equation that we have to use for molecular dispersion. So here this is because 2D or 3D is replaced by a 1D equation, and there is that apparent diffusion, which is called the hydraulic dispersion here. So this is possible to solve that equation with the right U, which should be transient as well, and that kind of term for the dispersion and the molecular diffusion as well. I have worked a lot with the water age, the residence time, and when we are transporting or calculating the water age, one problem comes from the mixing at the junction nodes. In EPNet and other software, this is usually the flow rate average, which is done. But what we found interesting in some recent research in Smart Online, for example, this is also interesting to calculate the mean of the water age at each junction nodes and the max. So with that, you understand the two limits, the lower limit and the upper limits for the water age. There are also a lot of uncertainty in the model, in the demand, in the roughness, for example. And this is interesting to understand the influence of that uncertainty. So here, this is a research that Matthias Born has done during his PhD. So the calculation is, for example, 10 hours for the water age, but if you look for the different possible error that you have in the system, in fact, what you get is the sampling distribution of the water age. In some case, there is only one mode. In different case, you could have two modes, meaning that here there are different paths for water in your system. So for water age, we found useful to calculate the mean and max, but also to understand the uncertainty of the water age and more maybe the distribution. We talked about already during our committee for the risk of Legionella. For cold water, this is recommended to have the water below 20. Hot water, this is above 55. But when we want to design and understand a complex building system, as Phil has the experience, we need the use of modeling and also the use of hydraulic modeling for thermal calculation. I will give you some example. So here, this is a calculation of the kinetic viscosity. So this is interior promise plumbing with 3 centimeter inner diameter, length 200 meter. The internal roughness millimeter is 25, and here this is the flow velocity. This is the Reynolds is about 4,000, 5,000. So this is turbulent. And this is the frictional factor, the Darcy-Weber factor that we calculate with the Colebrook equation here, and the L loss that we get. And as you can see, the temperature play a role, of course, for the head loss that you have. Another example is about also the temperature and the travel time. So this is the same example with 200 meters, and the travel time is 20 minutes. Here, this is an example of the thermal conductivity, so the heat loss that you have in your tubes. And you can see that the temperature grew until 56.9, so there is a loss of 3 degrees during the system. So we have to use and understand how to improve the system. And for some complex system, it could be difficult and a challenge. Here, this is an example in Germany. There are two basic systems for house. So this is not a complex system. It could be a loop system for hot water. So this is a circulation system. And here, this is more a three-branch system. And each system have cons and pro advantage and inconvenience that you can see. For the loop system, there is a good availability of hot water, but this is very energy demanding. For the tree system, you can make some economy of energy, but you have to wait for the hot water. In summary, our experience is that we need to have some slow transient model or rigid water column modeling inside the house as well. Even if we don't have the experience totally, we have to understand when we need to have that transient model, for example, for the toilet. This is very useful, especially inside the premise plumbing systems, to have the min-max envelope, lower and upper limit for the water age, and also to understand the impact of the insanity. We believe that the molecular diffusion should be assessed in the model as well. And the temperature is very important. So here are some questions that we would like to discuss if there is time and if people have experience for that. This is about the imperfect mixing inside the premise plumbing systems. What about if the water is not monophase, not only liquid and is multiphase? What about intermittent dissolution if there is roof tanks? This is more maybe simulation in Africa and some country around the Mediterranean. What about using fast transient for the design and relation force? Yes, this is not a question, and some speakers today feel is using fast transient to assess the design, so we need to have that. But what about the tools that are available? Are they suitable or not? Thank you for your attention.
Excellent. Thank you very much, Pilar. Appreciate it. So our next speaker will be Feng Sheng from USEPA, and then he will continue the discussion on the dispersion in premise plumbing.
Thank you. Yeah, I'm relatively new to this premise plumbing research, and today I'm going to talk about dispersion, as Pilar mentioned, in premise plumbing. First, I think people may wondering, yeah, maybe dispersion is a water quality problem. So why I talk in this hydraulics session, I try to justify that through the talk. First, today we are only looking at laminar flow conditions. So the laminar hydraulics is pretty well known. So in fully developed laminar flow, it's more like a parabolic profile velocity. And the velocity is the maximum at the center of the pipe, and almost like zero at the pipe wall. So the center velocity, basically the maximum velocity, is 2 times the mean velocity. So this is basically the basic hydraulics of laminar flow. And let's think about the transport in laminar flow. So if we have some contaminants or we have some what are called constituents released at the beginning, at the like start of a pipe, these constituents will travel with the flow, basically carried along with the flow, and they also will move in the radial direction because the velocity difference will create a concentration gradient for this kind of species. So basically we have 2 mechanisms here, right? We have advection of constituents due to different velocity. In the center of the pipe, the constituents travel further than the constituents close to the pipe. So this is the random walk of constituent basically due to the molecule diffusivity. As Pilar mentioned, Sir Taylor, he had this famous formula to use 1D advection dispersion equation to model this kind of mechanism. So this E here is it's called effective dispersion coefficient, or it's called hydraulic dispersion coefficient. And the value of this dispersion coefficient can be calculated based on pipe radius A, mean velocity U, and molecule diffusivity D here. But there are conditions to apply this kind of formula. The time need to be long enough. So given enough time, 1D advection dispersion equation can describe the constituent transport. Because this transport mechanism, as I showed before, is indeed a 2D phenomenon or even 3D phenomenon. But this 1D equation, in order to apply, we have to have enough travel time. And how long the time can be? So for like half-inch pipe, and with typical diffusivity of 10⁻⁹ square meter per second, the T is like 30,000 seconds. So the pipe needs to be very, very long for this kind of equation to be applied. And we don't think it's the case in premise plumbing, right? So there is some revision to Taylor's formula. The theoretical basis is that the mean and the variance of the species concentration distribution actually can be calculated analytically. So there is a classical paper by Gill in 1970, and Yang Ho Lee, he got his PhD in University of Cincinnati, Steve Buckerberg's student. He gave an excellent approximation of this effective dispersion coefficient when the time is shorter than what's required in Taylor's formula. But what happened in very short pipes, like in like premise plumbing case, maybe 10 meters, 20 meters, this kind of pipe, or even 5 meters? Does the 1D advection dispersion equation can be applied or not? And we think computational fluid dynamics tool maybe is needed to study the details of the concentration profile of the species or constituents within the premise plumbing system. I looked around and I find this called the Lagrangian particle tracking method is very interesting. It can be very complicated. It can even model like a multi-phase flow, but I'm here using it in a very simple kind of naive way. So basically, first we can generate lots of particles to represent the species or constituents or pollutants at the source, or here is the beginning of the pipe. Then we carry this particle along with the flow because we know the hydraulics of the pipes. And then the particles move randomly in this 2D cross-section based on molecule diffusivity. Basically, it's Brown motion. And we know the molecule diffusivity, we know the time step, so we can, let them just move in Monte Carlo kind of manner. We don't need to calculate the effective dispersion coefficient. which is quite hard, as I showed before, especially when the time is short. So then I can talk a little bit about the process. So first, you can generate lots of particles, and this is a half-inch pipe kind of. So I generated like 10,000 particles at the source. Then we can do as a normal water quality simulation for each quality time step, move these particles along the velocity streamline. Then do the molecule diffusion by randomly sample based on the diffusivity. So basically to mimic the Brown motion. In order to check if it's really doing what expect to do, first I look at the classical Taylor's case when the dimensionless time is large. Here basically you can see the time is very large, like 50,000 seconds. So with like 0.1 meter per second velocity, half-inch pipe, the Reynolds number is like 1500, is within the laminar flow range. So I assume that 100 gram pollutants is released instantaneously at the beginning of the simulation. I use 100,000 particles to mimic it. So you can see the brown kind of orange line is the Taylor formula, and the blue is basically the particles, distribution along the pipe at that time. It seems to match pretty well. One is pure kind of Taylor formula, is you see it's a Gaussian distribution, a bell shape. The other is the kind of Monte Carlo simulation with the particles. I didn't smooth out the numerical results, so you can still see maybe some outliers, but that should be expected for numerical analysis. Then let's see when the time is shorter. Not that shorter, it's still 5,000 seconds, but the dimension time is 0.1, and it's shorter than the requirement for Taylor formula. You can see they still match pretty well, but I'm here using Yang-Ho Lee's approximation for this effective dispersion coefficient. You can see the spread is still very similar comparing the Lagrangian particle and the 1D advection dispersion formula. But the shape is different because 1D advection dispersion, basically it's mimic the kind of Gaussian distribution of the pollutants or species. But in reality, there is skewness of the distribution. So the Lagrangian particle method show the skewness of the distribution. Now let's see when the time is really, really short, like in kind of premise plumbing condition. So here I assume like I look at 35 and 70 seconds cases. So when the simulation time is 35 seconds, with 0.1 meter per second, basically it's travel 3.5 meters, right, in average velocity. And for 70 seconds, it travels 7 meters in velocity. But as I mentioned at the beginning, the laminar flow, the maximum velocity is 2 times of the average. So for 35 seconds with 0.1 meter per second, it actually travel up to 7 meters. And in other cases, it travel up to like 14 meters. But look at the Lagrangian particle tracking. The shape is not Gaussian at all now. So meaning 1D advection dispersion equation cannot mimic or simulate this kind of shape, no matter what kind of effective dispersion coefficient you are going to use. And more interestingly is like the species concentration is kind of flat in this kind of travel range. First, I thought I did something wrong. Why is this happening? It doesn't look like diffusion at all. Then I look into literature in like chemical engineering science or general fluid mechanics. People have talked about these things. So when the Peclet number is large, which is in our case, meaning the velocity is higher comparing to the molecule diffusivity. And when the travel time is very short, it will happen this way, because when the time is very short, molecule diffusion won't cause much difference because the time scale is too short and the molecule diffusivity is pretty small. So that kind of explains why this happened. So in the Lagrangian particle tracking, I just remove the molecule diffusivity or the Brown motion part, and I just try to calculate the constituent transport due to velocity file. Remember this parabolic laminar flow velocity profile? And we can see the results with and without molecule diffusion is very close, actually, especially for this 35 seconds and the travel distance 7 meters case. It's almost same. But for this 70 seconds case, we see a little bump here. I'm pretty sure this is caused by molecule diffusivity. Why exactly? I'm not sure. So I haven't looked really into the mechanism of it. So here we can see the diffusion impact is almost negligible for this kind of very short travel time case. Again, the travel velocity, flow velocity, mean velocity is 0.1 half-inch pipe. Here, because the travel time is very small, I assume it's 1 gram, and I use 100,000 particles to represent this 1 gram of pollutant or even disinfectant, any species basically. Right. So then the take-home message, I think, in short pipe that is typical in Krebs plumbing, the molecule diffusion may have little impact on constituent transport results. Velocity profile is the determining factor for constituent transport. So that answered the beginning question. So I think dispersion in Krebs plumbing is a hydraulic problem. So that's why I think, I can talk this in the hydraulic session. And I just try some very naive Lagrangian particle tracking as a CFD approach. But I think the promise there is likely a good tool to do the analysis. First, I think the most important is really easy to understand. I don't even need to look into the partial differential equation. I don't need to worry about the the mesh, and it also can handle different kind of boundary conditions easily. For example, I can release all the particles uniformly in the cross section, or if the intrusion at the center of the pipe, then all the particles can be released at the center. And it's easy to implement as I show. And we all know Lagrangian method has little numerical diffusion. Most importantly, not most importantly, numerically very important, it's very suitable for parallelization. So you can generate 1 million particles, and you keep track of them individually. This is a disclaimer I have to show. So basically the summary, I guess, the classical 1D advection dispersion equation with effective dispersion coefficient likely doesn't apply to premise plumbing. CFD analysis can shed some light on the details of the transport process in this small space and time scale as in premise plumbing. Flow condition other than fully developed laminar flow should be considered. It shouldn't be that hard, because if we know the velocity profile of turbulent flow or turbulent diffusion, I think a Lagrangian particle method can still apply. Of course, combination of detailed experimental and numerical analysis is needed to really look into how contaminant will transport in premise plumbing condition. That's it. Yeah, thank you.
All right. Thank you very much, Feng. Excellent presentation. Appreciate it. So now we are going to switch gear to the demand forecasting and with the machine learning, and also its implication for the hydraulic modeling. Zoran, the floor is yours.
Thank you, Jun-Sok. Hello, everyone. Hope you can see my presentation, the title slide.
Yes, very good. Thank you.
Okay, thank you. So now in the words of Monty Python, something completely different. This presentation is not so much about hydraulics, it's more about demands, forecasting and understanding these demands using interpretable machine learning. And of course, we want to do this for a number of different reasons, including improved hydraulic modeling. What was the data used in this work? This is based on a PhD that was 4-year PhD, which was completed last year in the, 2 years ago in the UK. There are two main sets of data. Demand data was smart demand metering data available at 30-minute intervals, and this was provided by the West Export Company in the UK. It was available for 3 years, and in addition to these detailed smart demand metering data, there was some data on households and other data related to the occupants of the households, and I'll mention this in a minute. In addition to this, we use the publicly available weather data, which is from the Met Office in the UK. The map here shows the location of these properties, which as you can see have been pretty much scattered around the south and west of England. And on the right-hand side, you can see the basic statistics of weather variables, which is pretty much UK climate. Demand forecasting, a number of these models were developed. There were 4 principal groups of parameters which featured in these. So these were the output was the future consumption 1 to 7 days ahead. There were 4 principal groups: past consumption, what we call temporal, household, and weather. Temporal is really to do with the day. Is it a working day or week day? Is it part of certain month or season? The household data was available up to a point. Anything from acorn data, which is really about the social affluency of the people who live in the properties, categorized anything between socially affluent to financially stretched. Garden size, existence and size, metering status, because not all properties were metered ideally. Rateable value and council tax band, these are basically some government data on the value of properties, which then is indirectly related to the consumption as well, to the size and the consumption, and occupancy rate. And of course, in terms of weather, we had all the basic variables. A number of these methods have been developed using some advanced machine learning techniques, ranging from random forest, gradient boosting, and so on. This data was different combinations of inputs were used from the previous slide, and we developed some eight models made out of these different combinations of 4 principal types of inputs, and the households were grouped in a different way. There were 3 cases, basically what is called the network data, which is all properties together, but with a daily level of data, and that's why the variable number of households, because not all households had data demand recorded in all days. Areas, and why this called network still beats me. I guess it's a mystery which can only unlock by asking the PhD student. The areas grouping, the middle one is basically grouping the households based on the first part of the postcode. So in the UK, this normally means part of town. And then the final one, which is called here district, is based on the full postcode, which is typically a neighborhood level houses. So in the districts, you have typically several tens of houses. In the areas, you have up to 212, and in the network even more. So what are the results? In terms of machine learning methods, they all did reasonably well. The most accurate one was the stacked one with bias correction. Stacked means ensemble model. Having said this, it's basically an ensemble of a number of these other models. It's very computationally demanding, and I personally think the gradient boosting machine, which is quite novel machine learning method, did actually probably the best in terms of trade-off of prediction accuracy and computational time. In terms of further results, in terms of model inputs, and this is where some interesting insights can be gained about the demand, is first of all, unsurprisingly, model with all inputs, with all 4 categories did the best, and that's the model 1 in all these 6 figures. By the way, in these figures, you see mean annual percentage error as a function of forecasting horizon, 1 up to 7 days. For different models, 8 models. The top row shows the predictions for all days of data. So basically, average consumption. For all days, and then the lower row represents the peak days, the forecast for peak days. And you can see basically the network areas and districts, again, different household groupings. The other interesting insight was that forecast for all days, unsurprisingly, was more accurate than peak days. So you can see this if you compare the top and lower graphs, probably because the job is a little bit easier and there was a bit more data for the all days case. And another interesting insight was that when past consumption was not available, credible forecast could be made. So if you compare models 1 and 5, in these graphs, you will see that they are not too far away from each other in terms of accuracy. And this is an interesting finding for the water company, which means they can basically make credible forecasts even when they don't have the smart demand meter data for those kind of properties. Contribution of weather was rather limited, which is not that surprising given the UK climate, and you can compare this by models 1 and 3, but I will say more about this later on. And of course, the most accurate forecasts were obtained for the highest level of aggregation, which is the network. We did check this household aggregation in a bit more detail. So in addition to those three principal groupings, spatial aggregations of households, we created groups of anything between 5, 20, 40, 120, all the way up to 600 households. And when you plot the mean annual prediction accuracy or error as a function of number of household, as a number of household group size, this is what you get. So basically, as we kind of all intuitively felt, as the basically household group size reduces, the error increases. But according to our best knowledge, this is probably one of the first attempts that can quantify this, that can put a number to different household groupings. This, of course, has implications for hydraulic modeling. For example, if you want to group a relatively small number of households on a network node to do the hydraulics, then you can expect to get lower accuracy or higher error than for the larger ones. And the way these groupings are typically done nowadays in hydraulic models is different, and basically most people assume they just do the predictions, the forecasts for the whole part of town or the whole network, and then just allocate based on previous demands, which of course is, as this graph shows, is not the same thing. Impact of weather on consumption. When you look at all data, it's relatively moderate impact. Here you see the consumption liters per property per day as a function of air temperature, which was the most significant variable in radiation up to a point. This is the daily maximum temperature. This impact is a little bit more pronounced on summer evenings. So basically during peak time water consumption, probably because people use more water for gardening, possibly for showering as well. But again, this is UK climate. It's this impact of weather on consumption is relatively moderate. Similar conclusions were obtained based on some Dutch data, which Miriam Blocker from KWR kindly shared with us. And then we analyzed this on Italian data as well, which I haven't shown here. The impact there is a bit more pronounced, but surprisingly, it's not most pronounced at the peak of the summer. It's more kind of late spring, early summer, probably because of the fact that most Italians go for a holiday in August. So basically, which has impact on the consumption, especially residential consumption. And finally, based on Italian data, we recently looked into the impact of climate change on consumption. So of course, you take a particular climate change scenario, which gives you the predictions of likely changes in air temperature or other weather variables. And if you transfer this into if you put this back into your model, you can get different changes in consumption. And on the left-hand side, you can see these changes based on the average seasonal demand. On the right-hand side for the peak week demand. Red and green are just different models that we used from our own work, forecasting models, and that's why the differences in values. But what you can see from these graphs is that on average, basically with a peak, when you talk about average seasonal demands, they are increasing up to a point. Of course, the further you go into the future, the more they're likely to increase. And these increases are not negligible, but they are not terribly high, at least based on this analysis. Having said this, the impact on the peak week demand, on the peak demands, is more pronounced. And this, of course, has implications on the design of these systems or the need to redesign them and to do the associated hydraulic modeling. Just some acknowledgements. Most of this work was done by Maria Xenocristo, who is now at Stanford, applying her machine learning skills in the biomedical field. In terms of summary and needs, machine learning, as I hopefully have presented here, can be used to forecast effective residential demands. Credible forecasts can be made without past consumption, which is important for the utilities to estimate consumptions at non-metered properties. Impact of weather and consumption is moderate in the UK climate and the Dutch climate. It's a little bit different in Italy. The air temperature is the most significant variable. And existing hydraulic models, this is not something I really went much into during this presentation, but I firmly believe that existing hydraulic models need to be developed further to take advantage of latest demand metering data. I know some people are working on this in the field, especially in the real-time context, but it would be nice to see more of this work in the future. In terms of discussion questions, that's basically what I would like to discuss now. How can hydraulic models be improved to take advantage of latest demand metering data and forecasts? And we can also have a chat if we have time about the impact of weather and climate change on individual water uses. Especially, I'm keen on commercial and industrial side of things. I know that Steve Buckberger has been working quite a lot on characterizing industrial water consumption. So, thank you.
All right, thank you so much, Zoran. Excellent presentation, appreciate it. So, we're doing very good on timing. So let me share my screen. So, okay, so there you go. Again, quick advertisement. Our next monthly webinar will be water quality modeling of premise plumbing systems, and then that will be led by Jonathan Burkhardt from USEPA. And please mark your calendar. That'll be September 24th, 2020, the same time. So I trust we also have an excellent and very exciting speakers and then titles. So before we go into the Q&A session, so again, if you have any questions, please contact me. And also, again, thank you very much for the speakers. So we have starting from transient and also the practical applications, as well as the municipal water distribution network impact, and also another exciting topic, dispersions and the limitation of EPS, and also followed by the water demand modeling with machine learning, and also their impact on the hydraulic modeling. Thank you again for your excellent contribution for all the speakers, all very fascinating topics.